expert at image acquisition and analysis. We've talked a lot about common sense, and common sense is essential to keeping our feet on the ground and forming cogent understandings of the world that we live in. But we know also that our senses are somewhat limited. There's only so much that we can see with the eyes that we've grown in our bodies, that we can touch with our hands and our five senses. So science, when it's properly functioning and serving common sense, extends those senses into the realms beyond our ability to perceive, to, in a sense, make visible that which is there but is invisible to our common senses. And that is part of the expertise of our next speaker, an important part of what Pierre-ie Robitaille is accomplished at. In 1996, he was responsible for breaking essentially the world record for magnetic resonance imagery, developing essentially doubling the power of magnetic resonance with an 8 Tesla MRI. And I believe he's going to share with us some of what he sees to add to our growing sense of the electric universe. Welcome, Professor Pierre-ie Robitaille.
Thanks a lot. Well, thank you. I would like to begin by thanking Dave Talbot for inviting me here and for providing scientists from different viewpoints the opportunity to address the scientific community. It is a privilege to be here. Today I'll be speaking about the microwave background. And as Steve tried to explain to you, when you look at the microwave background, if you're located on the Earth, you have signal from the Earth itself, the emissions of the oceans, water around the Earth, and then you also have galactic emissions that are reaching the Earth. You have signals beyond the galaxy, perhaps, that we get to see as well. So there are many signals that are coming when you're at the Earth, but when you're at L2, the Earth, of course, cannot hit the satellites that are at L2. Therefore, you will not get a monopole at L2, and the only data, if you want to call it data, that you get at L2 will be dominated by the galaxy. Before I begin to speak, because I'm in the College of Medicine, I did want to speak just briefly about anchoring. Now, in medicine, what is anchoring? Anchoring occurs when a patient comes to the hospital and he's gravely ill. And we'll assume that he's gravely ill. And what happens is that a physician sees him and he decides on the diagnosis. But the diagnosis is incorrect. The next physician comes and sees him and doesn't do his own physical and follows the diagnosis of the first physician. So eventually, unfortunately, our patient dies. The doctors get sued, they lose their license, and of course the attorneys get to make lots of money. But what happens in physics when we anchor? Well, that's a different problem because we're not in a position that somebody's going to lose their life over it. At least we hope not. But when physics makes an error, it's much harder to rectify because you can anchor and it takes tremendous incentive to go back and recheck the assumptions. So relative to the microwave background, to recheck the assumptions, you actually have to go all the way back to 1860 and deal with Kirchhoff's law of thermal emission. Now, I will talk about that law on Sunday, not now, because it in of itself is actually the most important talk I will give, even though this one is on the background and the other one is on the sun. Also, because I'm in the College of Medicine, let's see now. I have to figure out how this works. I'd like to dedicate this work to two physicians. Now, the first is my father. He just retired from medicine after more than 50 years, I think 55 years as a physician. He was a family practitioner. He delivered over 800 babies in his life. He also helped the Sagamok Indians in northern Ontario. And he lowered the infant mortality rate for the Sagamok First Nations, both for the mothers and their babies. He was one of the first Caucasian men to be named as an honorary Indian chief in North America. The next, whoops, that's the mistake that we make. Okay, I'll get it here. The next person that I'd like to dedicate the talk to is Dr. Ignaz Semmelweis. Now, I dedicate it to him as well because he's got a lesson for us, right? So in 1847, he advocated that physicians wash their hands with chlorinated lime solutions to reduce the incidence of mortality from childbed fever. And physicians saw this as an insult because they felt that, you know, they were already pretty clean, even though they were going from the necropsy lab to delivering women. And they were killing these mothers. And he actually documented, when he got the doctors to wash their hands, that the mortality rates would drop. So the physicians, rather than just listen to him and keep washing their hands, decided that he had to be incorrect. His papers and ideas were largely rejected. There were only a few people of the European medical community that recognized the importance of what he was saying. He's actually, I think, the father of hygienic methods. And he unfortunately died in an insane asylum. He was only 47. Now, I've published extensively on the microwave background, and I list the papers here. Some of the important ones relative to the talks of Steve and I are WMAP, or radiological analysis, of course the papers on the Earth contribution, the paper on water, the bottom one that's listed there. Then you also have this all will affect global warming, whether you believe in global warming, don't believe in global warming. For us to understand how the oceans are actually emitting is an important problem. And then there's another paper on Kobe where I did a full analysis of Kobe, and one on Planck. Now, Dr. Rabunsky, who's the editor of Progress in Physics, has been very kind to me. He's taken many, many papers and enabled me to publish my work in what I consider a very new journal. And of course, people say, well, Pierre, why do you publish in Progress in Physics? And that's because it's a proper vehicle for what I'm dealing with now. Now, I also want to point out that there's some parallels between MRI and the microwave background studies. So an MRI scientist is actually well suited to go through this stuff because what we do are almost similar. There's only the sample that changes. In magnetic resonance imaging, it's fundamentally a thermal method. We have T1 relaxation. It's called the thermal relaxation constant. That was named so by Felix Bloch. Most people have forgotten that name. Their frequency of observation is from VHF to UHF. But the 8 Tesla that I built and new scanners are now at 0.4 gigahertz, so almost in the microwave. The detection methods that we use are RF antennas, and they're coupled to preamplifiers and radiometers. We display our results in spectral images. Now, if you look at the microwave background, again, you have a thermal problem. You have a maximum emission at 160 gigahertz. Of course, Penzias and Wilson were at 4 gigahertz in their first experiments. That's only, we are now at 0.4 in magnetic resonance. The detection methods are very similar at low frequency. In microwave experiments, we have RF antenna coupled to preamplifiers again and radiometers. And we display our results in spectra or images. So just generally, what are the requirements for having an image? Well, there's basically 2 requirements. The 2 key requirements is you have to have resolution, and you also have to have signal to noise. And it takes signal to noise to make contrast. It also takes signal to noise to get resolution. If an image is noisy, how can you tell if it contains any information? And this is critical to anybody who believes that the microwave background anisotropy maps can be real. For them to be real, they have to be reproducible. And none of these maps are ever reproducible. So they pool the data, and then their differences are from averages minus a year, or in Planck now they're trying to pool a bunch of data. So you can't take averages. You have to look, when you have a low signal to noise image, as you do in medicine. When we do functional imaging, for instance, we're going to have quite low signal to noise. Sometimes in the cath lab, you might have low signal to noise. And how can we tell that the signal is real? Because it has to be reproducible. So if you ever are encountering somebody who's telling you the anisotropy maps are real, just ask him for reproducibility. He will never be able to deliver it because the galaxy is too variable. Now, I want to show you an image that was done at the time that I did the 8 Tesla. This is an image, it's a clinical image from a human head. It's a sagittal slice. And this is done with a conventional scanner. It was a good scanner. The image looks really bad, and it's because I'm pushing the scanner right to its limit. So I'm taking a very thin slice, very little bit of the tissue, and the matrix size is a 512 by 512. With only a 2 millimeter slice. So when I do that, there's so little signal, you can't get contrast anymore. Did you remember I told you it takes signal to get contrast? So this is a 512 by 512. And now here's an image from 8 Tesla. And this is still a world record today, even though it was done for the year 2000. This was an image of 2,000 points by 2,000 in resolution. Same data, same slice thickness, similar nutation angle. Everything is very comparable between these two images. But the difference is, of course, I have more signal because I have an 8 Tesla scanner. So this remains, as I said, a world record in resolution. Here's an expanded view of that. So now, what are the central issues relative to understanding the microwave background? Well, I think there are several. The first is the early measurements. Did we have a right to assign the signal of Penzias and Wilson to the universe? Could water have produced this signal? And where is the water signal from the Earth? If the microwave background signal really belongs to the universe, where is the Earth signal? Does the 3 Kelvin temperature really have a real value, or is the temperature really only apparent? Now, this will be answered primarily in my talk on Sunday on Kirchhoff's law. Can we really see beyond the foreground of the galaxy into the universe? And is there any real cosmological information in the anisotropy maps? Did data processing produce the monopole? The multipoles? Steve touched on this. Has mankind truly sampled the first trillionth of a trillionth now of a second after the Big Bang? So we'll begin just by a quick review of the Penzias and Wilson experiment. And when they completed their experiment, they reported immediately that they had a 3.5 Kelvin signal that was unexpected. And there was this excessive signal was isotropic, unpolarized, and free from seasonal variations. Now, if you look at the way the horn worked, you had a contamination from the horn. The noise from the horn was only 0.9 Kelvin. But they assigned 2.3 Kelvin to an atmospheric contamination. So the total signal that came in was 6.7. Now, of course, they could rotate this horn, and that's how they determined the amount of signal that's coming from the atmosphere. They could just rotate the horn, and as they rotated the horn, they can compensate for this atmospheric signal. But what they don't compensate for is an oceanic signal that's pumping photons into the atmosphere. They also say that this 2.3 Kelvin signal was due to absorption by oxygen in the atmosphere. I think it had nothing to do with it. Nowhere in the Penzias and Wilson papers of 1965 can one find any discussion of water and where it might be expected to emit. Now, of course, they immediately say that a possible explanation is done by these cosmologists. Now, what happens in Astrophysical Journal, actually, is that this interpretation by Dike, Peebles, and Rolls and Wilkinson actually precede the Penzias and Wilson publication. So since when in science do we publish the finding after the interpretation? You publish the finding first, then you publish the interpretation. So in the interpretation, they say, well, could the universe be filled with microwave energy that behaves as a black body that gives us this black body signal? The answer, of course, is no. The assignment of a 3.5 Kelvin temperature constitutes a violation of the laws of thermal emission, and I will talk about that on Sunday, because that in itself is quite detailed to explain. But valid temperatures require a known solid, no net conduction or convection, or if you don't have a known solid, you must be in thermal equilibrium with a rigid, perfectly absorbing enclosure. Otherwise, the temperature obtained may or may not be accurate. So the universe is not in thermal equilibrium with an enclosure, okay? And especially if it's expanding. It had no chance of ever becoming in thermal equilibrium. A source which is not at 3 Kelvin can produce a signal if it sustains, in addition to emission, other means of contending with internal heat, namely conduction and convection. And this is, by the way, the reason that Max Planck said you cannot take a temperature of the sun using thermal emission. A source which is not at 3 Kelvin can produce a 3 Kelvin signal if it has an unexpected distribution of energy within its degrees of freedom. As a result, can water at 300 Kelvin produce a signal with an apparent temperature of 3 Kelvin? So I thought we'd start by just assessing the situation here. We're sitting on the Earth. I think there's quite a bit of water around us. Actually, this famous poem that many of us learned in grade school, The Rime of the Ancient Mariner, reminds us, water, water everywhere. Water has often complicated microwave background experiments. So in their own literature, when you read their papers, you see that they're always having trouble with water when they're doing the experiments near the Earth. But they dismiss all this. For instance, when Dr. Smoot was testing a radiometer at Berkeley, he actually took the radiometer outside in the parking lot, and there was a cloud that went overhead, and he saw that he got a signal from the cloud, so he knew his radiometer was working. Of course, he was sampling water at the time. Then Rainer Weiss, he noticed that whenever you're doing microwave background experiments, it's very simple to do when there's oceans or lakes nearby. John Mather, he commented in his book that people working in the Atlantic Ocean had a very difficult time getting microwave background measurements done because the oceanic signals the oceanic patterns can produce signals that are very similar to cosmic fluctuations. And Dr. Woody noticed that he sent up a balloon, and on the ground and during the ascent, they protected the antenna from condensation. And then they had a small mirror to allow them to make sure that there was no condensation inside their horn. Well, if condensation doesn't matter, why do you care, right? Now, we know that condensation matters because Dr. Smoot, when he went to Lima, Peru with an experiment, and when he came down with the plane, he got condensation in his radiometers, and they didn't work. So what did he do? He took them apart. He took out all the water. He dried them up, put them back together, and all of a sudden it worked. Here's one from John Mather. The effect of air condensing into the antennas were seen. When the second window was opened, the valve which controls the gas flow should have been rotated so that all the gas is forced out through the cone and the horn. When the situation was corrected, emissions from the horn were reduced, and the cold helium has cooled the surfaces on which the air had condensed, and the signal returned to normal. So he's telling you, when I have water there, my signal was too high. Now, of course, as Steve pointed out, this slide from one of my papers, I'm just showing the structure of water, and to remind everybody that there's a hydrogen bond here, and this is not at all like a hydroxyl bond. The energy of this bond is about 100 times the energy of that one, the force constant. The force constant in this bond that is characterizing this bond, if we look at it as a simple harmony oscillator, the force constant here is 100 times stronger than that one. And that's a great concern. So if you look at it, if you look at the water dimer, which we know exists in the atmosphere, now I'm just taking the water dimer as an example. The water dimer, you can find it also in condensed water, in liquid water. If you look at the structure of liquid water, you'll see dimers inside of it. And if you compare, if you look at this, whoops, I'm sorry. I did a boo-boo. I will get there. So if you look on axis here, in the dimer, this is a linear, these three atoms are all arranged linearly. There is libation around this one, but generally you can assume that they're linear. And if you do that, you can easily show that the energy in system 1 divided by the energy in system 2 will just be equal to the ratios of their force constants. Now the energy is related to their temperature. Well, since these force constants are different by a factor of 100, then the emission that you'll get will be different by a factor of 100. So instead of getting 300 K emission, you get 3 Kelvin emission. So remember, if water is a powerful absorber of microwaves, then by Stewart's law, it's also a powerful emitter. Now, a brief note on the COBE satellite, which Steve also covered. So the Ferris horn was designed to operate over a phenomenal range, actually from 30 to 3,000 gigahertz. But no other microwave horn has ever claimed to cover such a frequency range, even 25 years later. The claim is unsupported by vast knowledge of practical microwave antenna design on Earth. It's an engineering impossibility. The COBE satellite, as Steve mentioned, is positioned at an altitude of 950 kilometers. But the shield, the satellite itself, or the horn within the satellite, which is located here, this shield has nothing to do with microwaves. This is a shield for thermal photons, not microwaves. If it was a shield for microwaves, it should be properly shielded. So here I will, for instance, in this case, what are you having? You're having photons coming down from the Earth below it, and they're coming up and they're hitting the shield and they're diffracting against it, and they come to the top of the door and they diffract right into this horn. Notice that the horn, the Ferris horn, has a very smooth wall. So because it has a smooth wall and because it's broadband, it cannot be shielded for diffraction. So it has no corrugated surface to prevent diffraction. So a horn, a narrowband horn in microwave that you would use to prevent diffraction would have walls that look something like this. So now you see this corrugation. And these corrugations that are put in horns, they're very frequency specific. That's why these are narrowband horns. You never would make such a horn for a broadband signal. So unlike the Ferris horn on COBE, which is broadbanded, corrugated horns are always narrowbanded. The geometry of the corrugation is carefully calculated to be effective over a very narrow frequency range. So there's no way the COBE satellite could have prevented diffraction. Actually, Wilkinson himself, who was a member of the COBE team, and for which the WMAP satellite is named after his death, was worried that there was diffraction in the COBE data. So one of their own team members was worried about it. So the COBE satellite, of course, is located just above a powerful source of microwave emissions, the oceans of the Earth. Clear signs of diffraction exist in the COBE Ferris data. The data is too high at low frequencies, too low at high. So the Penzias and Wilson signal is very likely to be produced by the Earth. Now we'll go through WMAP. Now I covered WMAP, and there's a lot of lessons in WMAP which actually applies to all their methodologies in trying to create anisotropy maps. Now, as I mentioned, WMAP is sitting far out in space. This is a picture of the satellite, and it's sitting over here at L2. So in this position, well away from the Earth. There's no way WMAP is getting a monopole signal from the Earth. and WMAP never saw a monopole signal. It's unable to by design. But Planck should have been able to see it, because Planck has the capability, should have had the capability to see an absolute signal. But they never reported a monopole signal from L2 with the Planck satellite. In fact, for Planck analysis, they use Kolbe-Ferris monopole data in their analysis. And that data, of course, is over 25 years old now, or nearly 25 years old. They also are worried that they have a lot of noise on their LFI. And my problem is that, remember that this is a high-tech device. Now that we got 25 years of high technology, we have a lot of noise coming into the LFI. But remember that Penzias and Wilson almost had no noise. They only had 0.9 Kelvin attributable to the instrument. Now, as Steve showed, here are the five maps from WMAP in each of the frequency bands. And of course, we see this enormous signal from the galaxy. Okay? Unfortunately, you can't get around this. This signal is actually much, much bigger than this. These are cleaned images where they've already processed the data to get rid of galactic signal out here because it was so high. The galactic center, this is a quote from their papers. The galactic center is 1,000 times brighter than fluctuations in the microwave background. And if you take this statement as real, it's impossible, absolutely impossible, to remove the galactic foreground and quantify any underlying signal. So here's an example from NMR. So if the cosmologists really think that they can do that, they can come and help us in medicine. So here's an example where I take a water signal, an NMR signal. So of course, water is 110 molar. So I'm going to take a sample. I'm going to make a sample of water, and I'm going to put a little bit of a compound in it, just 0.1 molar of this compound. Well, when I take the spectrum, which is A in here, all you see is the water line, okay? This is just water. I can blow it up, and when I blow it up a factor of 100, I now see some resonances from this compound. Now, the resonances are not below the water peak. They're next to it. But for the microwave background, they are under the water peak, the same. It's not water that they're looking at L2, but it's a similar situation. They're sitting over here under a strong, strong microwave signal. They got a little tiny signal. They have probably similar line shapes. They don't know what the line shapes are. It's absolutely impossible for them to resolve these two signals. It's a physical impossibility. So the problem for the microwave background studies is that the signal of interest is exactly at the same frequency as the contaminated galactic signal in every single channel. So under these circumstances, the galactic contamination of any magnitude cannot be properly addressed. How does one distinguish the galactic contamination from a constitution made by a primordial source? So now you got this enormous signal, and you have the primordial source, and you have now the primordial source. This little tiny signal. Well, actually very, very tiny compared to this. This is really off scale, right? I do have to use a slide here. So I have an analogy, okay? Paul and Mary may or may not be real. There's a bowl containing 6 cups of water on the table. How many cups of water, if any, did Mary pour in the bowl? That's the question they want to answer. All we really can tell is that there's a bowl with water on the table. That's as bad as my jokes get. Now, the situation is further complicated with WMAP with 300 known point sources. So now we've got a whole bunch of point sources that we have to take out of the map. So now we've got the galactic contamination, we got the point sources, and we got the galactic signal. Now for Planck, they've got 15,000 point sources. Well, try to put 15,000 point sources on this image, and you could basically build any image you want. So The problem for the microwave background studies is that the signal of interest is exactly at the same frequency as the contaminated galactic and point source signals in every single channel. In reality, there are millions of microwave point sources in the universe because every star can emit in the microwave and every galaxy can. These problems potentially exist at every single point in the map. When one looks at the anisotropy maps, all the points matter, even the points with near zero signal, because they are contained in the multipole analysis. Thus, the interfering galactic signal can be greater than the signal of interest by a very, very large amount, because the signal of interest can be close to zero. That is why the galactic signal can be viewed as contamination of 100, 1,000-fold or more. So this is shown here. You have your map, and you're resolving this in these multipoles. Now, these are the poles that they really care about in cosmology. They don't care about this map. They care about this stuff. But this stuff has positive and negative contributions. That means you're going through zero, right? So all the points, even the points close to zero, are extremely important, and you have no signal to noise. The entire assembly of laboratory experiments, we'll say even in medicine, demonstrates that it is not possible to extract a weak signal from a powerful overlying contaminant unless the experiment has perfect knowledge of the signal strength involved or the ability to control the signal at the source. It is physically impossible to remove the galactic foreground. So how does the WMAP team do it? Because I've just said it's impossible. Well, they use different methods over different years. However, the methods have nothing that can salvage the underlying problem. So I just want to highlight again what the maps really look like. So this is the 5 channels down in the lower part of the page of the slide. And in the middle over here, you have these the 3 on the right, the Q, W, V, and W band, shown again at lower resolution. But here's what they look like before they're cleaned. Now, do you see how much there was galactic contamination before it's cleaned? See how it looks when they present it to us? This is what people typically see. They don't realize that Q band actually has that much galaxy in it. And they don't even show the other 2 because they're going to be red. Now, how do they get rid of the galactic foreground? Well, this is a great experiment. What you do is you break up the signals in 11 regions, some away from the galaxy, which you call region 0, and then 11 regions in the plane. So I guess 12 regions total. So what do they do? Well, they're going to do some addition here. They've learned some algebra. So what they do is they take signal K and they negate it. And then they add it to Ka. They negate Q. They add V. They add W. Now, this is what they did in region 4. Now, in the adjacent region, this is what they did. So you see that the coefficients are completely different. They're changing by a factor of 1,000% in 2 regions adjacent to one another. But the reality is you're not allowed to negate this signal. All negations constitute a violation of the laws of thermal emission, as they make a cool sky appear warmer in the galaxy. In addition, one can be violating the 3rd law of thermodynamics, because when one inverts these signals, he can mathematically create negative temperatures which are prohibited. Temperatures do not exist below absolute 0. Just imagine if there is no monopole at L2. Now, in magnetic resonance, I'll confess that we can have negative temperatures because we can have spin populations and invert them. So we can talk about negative temperatures in our spins. They don't get to touch the galaxy. So here's what is happening. Now for region 0, look what they're doing. Each channel is either positive, as they choose to make it. There's infinite number of combinations. We can all sit down and come and take a sum to add to 1 and pick any numbers you want. As long as they add to 1, it's a valid solution. So what have they done? It's positive. This term is negative, okay? Then negative again, then positive. But look, remember I told you the data has to be reproducible? Look at the coefficients that they use for addition. See how they're changing over the years? This one has changed 43%. That's a big change in the same region. And by the way, the 3-year average contains year 1. So, when one inverts the channels, you're creating the multiples. You're creating these negative temperatures, and you are in violation of thermodynamics. So what is the signal to noise in the WMAP images? So people see, they see these images, oh my God, this is a real image. We've imaged the universe. That's because they don't really understand what is an image. So this is this famous image after the removal of the galaxy. Now here's the noise that they plot in their paper. So they give us a noise of plus or minus 100 microkelvin at this resolution. And we know that their images, were at plus or minus 200 at this resolution. These, I can't remember, I don't think these are identical resolutions. But you can gather from their data, if you look at it carefully, they have signal to noise of about 2 to 1 relative to the noise of their instrument. Now, I just want to show you some MR images of things, or different images. We won't say they're all MR. So what's the first one right here? I want you to guess. This is a 2.1 signal to noise, 2 to 1 signal to noise image. This is an actual image, probably of my head. This one is of importance to us here. This is an image of the moon. And this one, no one will guess. It's the image of my right hand. So when you have no signal to noise, guess what? You don't have an image, unless it's reproducible. And their image is not reproducible. So since the WMAP images are not reproducible from year to year, this is seen in the need to take different images at lower resolution, which you're not allowed to do. When you take a difference, it has to be at the same resolution, because this makes things look better than they really are. And their coefficients are changing from year to year. So here we have year 1. We have the 3-year average. Now, this 3-year average actually contains year 1. But when you take the difference of these, this does not look too good. Because now you had to degrade the resolution. Well, when you degrade the resolution, you lower the scale, right? This 30 doesn't mean anything now, because this is on a different resolution. See how big the blocks are versus the tiny points here. You have to keep the resolution the same. So actually, these two images don't agree at all, even though this image contains that one. So that gives you an idea how bad it is. So to give it in a different perspective, I did a color difference map with the resolution preserved. So in this case now, I'm taking the 3-year average, which again contains year 1, and I subtracted from year 1. Do you see all the leftover? And I can blow it up for you, and you can see that there is a lot of leftover, and some of this signal is red. So the difference image indicates that the data has nothing to do with cosmology, because these maps are not stable from year to year, let alone on a cosmological timescale. So if you have a point that moves, remember, we're measuring a signal that is not supposed to have moved. The universe, they tell us, is 13 billion years old. So it doesn't move on a year-to-year basis. So in order to make cosmological interpretation, the WMAP images must be perfectly stable from year to year. Even fluctuations at the level of a few pixels is disastrous. And it's a lot more than a few pixels, since the data must be stable on a cosmological timescale. So this is an impossible experiment. It cannot be done. Now, if you look, they also give us new analysis of the foreground, and they actually try to tell us, well, this galactic signal, I could break it into free emissions, spinning dust, thermal dust. It doesn't matter. It's all galaxy. Now, the Planck satellite. I wrote a paper on the Planck satellite, which Steve talked about the conduction out of the 4K reference targets. Well, when you have a conductive path out of a black body, it's supposed to be a black body, it doesn't need to emit any photons to get rid of its heat. It can use conduction. So conduction is strictly forbidden. So the satellite isn't even designed properly. The combination of data collected at all of Planck's 9 frequencies, this is a quote from them, is crucial to achieve the optimal reconstruction of the foreground signal. In order to subtract them, violate thermodynamics, and reveal the underlying cosmic microwave background. So now we have 9 signals with Planck, and now we're going to play the subtraction game with these guys. I don't care how they subtract it. You cannot invert any of these, because these have real physical meaning. Oh, and we have our 15,000 point sources now, and they tell us it's ripe for follow-up characterization. So here are my conclusions. Penzias and Wilson are not allowed to assign a temperature of 3.5 Kelvin to their signal. They don't know the temperature because they don't know that the source adheres to the conditions by which the laws of thermal emission can be applied. The applications of the laws of thermal emission in obtaining a real temperature requires that the source be enclosed with a perfectly absorbing enclosure, or that it be a solid. And furthermore, to have a thermal spectrum, you need a vibrational lattice, as you find in condensed matter. And in the Big Bang, there will never be one. As such, the 3.5 Kelvin temperature is not real. It's only an apparent temperature. And we have no evidence that the measured signal properly samples the entire energy content of the source. Because if you think of water, water can put some energy in the hydrogen bond, it can put some in the hydroxyl bond, and we know from the oceans that there can be a lot in convection currents. So the temperature assignment stands as a violation of the laws of thermal emission, since Penzias and Wilson cannot ascertain that the source of their signal was devoid of the effects of conduction and convection. That is, that they properly sampled all the degrees of freedom of the system in which they're interested. Also, relative to the monopole, given the chemical nature of the hydrogen bond and its proven ability to emit in this frequency range, we know that, as Steve mentioned, from microwave ovens. Our submarine commanders know it because as soon as they break the surface of the sea, microwave is dead when they go underwater. That shows that the oceans are very, very powerful absorbers. It is certain that the monopole signal arises from the oceans and that other water-containing bodies on our planet. There is no monopole at L2. This implies that the Earth cannot emit as much radiation in these frequency bands as some might believe. That has consequences for those who are interested in radiative balance of the Earth and everybody who's now absorbed with global warming. So it's important to reassign the signal because humanity cares about its proper assignment. This signal belongs to geophysics, not cosmology. Now, of course, we do have galactic signals, source signals, which we also sample from the Earth, but we don't care about those because they have no meaning. They have no meaning in cosmology, and they have no interest relative to understanding the Earth. The central signal that Penzias and Wilson won the Nobel Prize for, and that signal is still tremendously important, and believe me, I still believe they get their Nobel Prize. That was a great discovery, but the thing is, it has been misassigned by others, and now it has to be reassigned, and this is an example of improper anchoring in physics. Microwave signals come primarily from our own galaxy, and the billions of galaxies found in the universe, the point sources are innumerable. This is relative to the anisotropy maps. The microwave anisotropy maps have no meaning in science. So we repeat it. The microwave anisotropy maps have no physical meaning in science. They represent signal processing errors and artifacts, violations of thermodynamics. It is scientifically inappropriate to negate some microwave signals and then use those results to remove the foreground. This creates images with both positive and negative signals or temperatures, something never found in nature. It constitutes, at the minimum, a violation of the laws of radiation, and at worst, a violation of the third law of thermodynamics. Once again, multiples have no physical meaning in science. The anisotropy maps are devoid of year-to-year stability required of a signal of cosmological importance. Steve also talked about the axis of evil. So the axis of evil, which has been a subject of recent discussion in cosmology, is nothing more than image processing artifacts, which arises from an attempt to remove the foreground and create the multipoles. The Copernican principle remains valid. We do not live in a geocentric universe. So even though I said the water signal comes from the Earth, I'm not doing cosmology here. I'm just telling you the oceans are emitting in the microwave. We do not live in a geocentric universe. We have never seen and will never see the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Thank you very much. Affect global warming, whether you believe in global warming, don't believe in global warming. For us to understand how the oceans are actually emitting is an important problem. And then there's another paper on Kobe where I did a full analysis of Kobe and one on Planck. Now, Dr. Rabunsky, who's the editor of Progress in Physics, has been very kind to me. He's taken many, many papers and enabled me to publish my work in what I consider a very new journal. And of course, people say, well, Pierre, why do you publish in Progress in Physics? And that's because it's a proper vehicle for what I'm dealing with now. Now, I also want to point out that there's some parallels between MRI and the microwave background studies. So an MRI scientist is actually well suited to go through this stuff because what we do are almost similar. There's only the sample that changes. In magnetic resonance imaging, it's fundamentally a thermal method. We have T1 relaxation. It's called the thermal relaxation constant. That was named so by Felix Bloch. Most people have forgotten that name. Their frequency of observation is from VHF to UHF. But the 8 Tesla that I built and new scanners are now at 0.4 gigahertz, so almost in the microwave. The detection methods that we use are RF antennas, and they're coupled to preamplifiers and radiometers. We display our results in spectral images. Now, if you look at the microwave background,
he sees to add to our growing sense of the electric universe. Welcome, Professor Pierre-Marie Robitaille.
Well, thank you. I would like to begin by thanking Dave Talbot for inviting me here and for providing scientists from different viewpoints the opportunity to address the scientific community. It is a privilege to be here. Today I'll be speaking about the microwave background. And as Steve tried to explain to you, when you look at the microwave background, if you're located on the Earth, you have signal from the Earth itself, the emissions of the oceans, water around the Earth, and then you also have galactic emissions that are reaching the Earth. You have signals beyond the galaxy, perhaps, that we get to see as well. So there are many signals that are coming when you're at the Earth, but when you're at L2, The Earth, of course, cannot hit the satellites that are at L2. Therefore, you will not get a monopole at L2. And the only data, if you want to call it data, that you get at L2 will be dominated by the galaxy. Before I begin to speak, because I'm in the College of Medicine, I did want to speak just briefly about anchoring. Now, in medicine, what is anchoring? Anchoring occurs when a patient comes to the hospital and he's gravely ill. And we'll assume he's gravely ill. And what happens is that a physician sees him and he decides on the diagnosis. But the diagnosis is incorrect. The next physician comes and sees him and doesn't do his own physical and follows the diagnosis of the first physician. So eventually, unfortunately, our patient dies. The doctors get sued. They lose their license. And, of course, the attorneys get to make lots of money. But what happens in physics when we anchor? Well, that's a different problem because we're not in a position that somebody's going to lose their life over it. At least we hope not. But when physics makes an error, it's much harder to rectify because you can anchor and it takes tremendous incentive to go back and recheck the assumptions. So relative to the microwave background, to recheck the assumptions, you actually have to go all the way back to 1860 and deal with Kirchhoff's law of thermal emission. Now, I will talk about that law on Sunday, not now, because it in of itself is actually the most important talk I will give, even though this one's on the background and the other one is on the sun. Also, because I'm in the College of Medicine, let's see now. I have to figure out how this works. I'd like to dedicate this work to two physicians. Now, the first is my father. He just retired from medicine after more than 50 years, I think 55 years as a physician. He was a family practitioner. He delivered over 800 babies in his life. He also helped the Sagamok Indians in northern Ontario. And he lowered the infant mortality rate for the Sagamok First Nations, both for the mothers and their babies. He was one of the first Caucasian men to be named as an honorary Indian chief in North America. The next, whoops, that's the mistake that we make. Okay, I'll get it here. The next person that I'd like to dedicate the talk to is Dr. Ignaz Semmelweis. Now, I dedicate it to him as well because he's got a lesson for us, right? So in 1847, he advocated that physicians wash their hands with chlorinated lime solutions to reduce the incidence of mortality from childbed fever. And physicians saw this as an insult because they felt that, they were already pretty clean, even though they were going from the necropsy lab to delivering women. And they were killing these mothers. And he actually documented, when he got the doctors to wash their hands, that the mortality rates would drop. So the physicians, rather than just listen to him and keep washing their hands, decided that he had to be incorrect. His papers and ideas were largely rejected. There were only a few people of the European medical community that recognized the importance of what he was saying. He's actually, I think, the father of hygienic methods. And he unfortunately died in an insane asylum. He was only 47. Now, I've published extensively on the microwave background, and I list the papers here. Some of the important ones relative to the talks of Steve and I are WMAP, or radiological analysis, of course the papers on the Earth contribution, the paper on water, the bottom one that's listed there. Then you also have this all will affect.
He's expert at image acquisition and analysis. We've talked a lot about common sense, and common sense is essential to keeping our feet on the ground and forming cogent understandings of the world that we live in. But we know also that our senses are somewhat limited. There's only so much that we can see with the eyes that we've grown in our bodies, that we can touch with our hands and our five senses. So science, when it's properly functioning and serving common sense, extends those senses into the realms beyond our ability to perceive, to, in a sense, make visible that which is there but is invisible to our common senses. And that is part of the expertise of our next speaker, an important part of what Pierre-ie Robitaille is accomplished at. In 1996, he was responsible for developing, breaking essentially the world record for magnetic resonance imagery, developing essentially doubling the power of magnetic resonance with an 8 Tesla MRI. And I believe he's going to share with us some of what